This is video 4 in a series of videos I made for my honors chemistry class about chemical bonding, and this video is about metallic bonds. And metallic bonds are the bond that holds together neutral atoms in a metal. And it's important to realize that we're talking about atoms here, not ions. And recall that ionic bonds hold together ions, and covalent bonds hold together neutral atoms also. But covalent bonds, the neutral atoms involved are nonmetals, whereas in a metallic bond, clearly the neutral atoms involved are metal atoms. So what is the force that holds together metallic bonds? It's our good old electrostatic charge attraction once again. And this time we need to focus on what the plus and the minus is in that opposites attract interaction. If we go back and think about our ionic bonds, our plus and minus were ions and the cations and the anions. If we look to our covalent bonds, our positive side was the nucleus of the atom, and the negative side was the shared electrons. This time, what are our plus and minuses? Plus and minuses, we need to look at our mental conception of metallic bonds. First, the key to understanding metallic bonds is to realize that atoms of metal hold onto their valence electrons very weakly. And if we remember our trends, that as I go to the left on the periodic table, I have a lower effective nuclear charge, and as I go down on the periodic table, I'm larger, more energy levels, not holding your electrons as tightly. So the metals in general hold their electrons very weakly. So the mental picture that we will use of metallic bonds is as a metal cation in a sea of valence electrons. And that's what all these pluses are here, we picture the cations of the metals, and then here is the sea of valence electrons all throughout these. And each metal has sort of lost the identity of their valence electrons. And those valence electrons are moving about between the atoms. So they're not particularly associated with a particular metal anymore. And here's another way that we can visualize this, that each one of these represents the nucleus of a metal atom, and we have a few different rings here representing electrons, and all of the little V's here are my valence electrons that are not associated with a particular atom, but rather they are free to move about between the atoms. But it's important to always keep in mind of our mental picture versus the reality. Remember, although we use the picture of metal cations attracted to a sea of valence electrons, a metallic bond is actually between neutral atoms. So we just use the mental conception of it being cations in a sea of valence electrons. It really is neutral atoms. The valence electrons are highly mobile and are not associated with one particular atom. So back to my question of earlier, what are my positive and negative of the electrostatic charge attraction? And the positive would be our mental picture of the metal cations, and our negative side that they're associated with is the sea of valence electrons. All right, so when we think about some properties of metals, our mental picture of the atomic structure of metals helps explain these properties. So we'll start off with conducting electricity. If we recall, electricity is just the flow of electrons. So as electrons flow into the metal, the mobile valence electrons flow and leave the metal, replaced by electrons from the flow of electricity. So finally, we have a path for the electrons to travel through. If we think back to our ionic bonds, they did not conduct electricity because each one of those ions involved was holding onto their electrons fairly tightly and did not have a pathway for the electrons to flow. Here the electrons do flow, and I think it's sort of an interesting point that as the valence electrons flow and leave the metal, they're actually replaced by new electrons. Alright, so my next property of malleability and ductility. When force is applied to a metal, the repulsive forces between the oppositely charged ions, like in an ionic bond, are not generated here. Remember, everything is the same element. There are not metal cations and nonmetal anions. And the sea of valence electrons facilitates the movement of these layers, sort of like ball bearings, allowing those different metal atoms to slide across one another. So when we apply force, the metal is malleable and ductile, unlike our ionic compounds, which were brittle. And here's a visualization of this. Here I have an ionic compound with my regular arrangement of cations and anions and cations and anions. And when force is applied, I get like charges that will line up with one another. And you end up getting breaking. Therefore, my ionic compounds are brittle. However, when I look down here to my metal and I apply my force to the metal, that I have the same charged ions all along the way. So all they do is they slide right across the top of one another, and I don't generate those same repulsive forces. Looking at the actual crystalline structure of metals. So like ionic compounds, metals have a very regular, organized arrangement of the atoms. In this case, an arrangement of the atoms is atoms, not ions here. So examples of these structures you can see in your textbook on page 202. We have structures like body-centered cubic, and face-centered cubic, and hexagonal close packed, and there are many more. It's not going to be a really focus of this particular class, but we'll take a look at these during class. We'll see the particular body-centered, face-centered, and hexagonal close packed. All right, another thing associated with my metallic bond is the concept of alloys. And an alloy is just a mixture of two or more elements, at least one of which is a metal. So it does not have to be two or more metals, we just need one metal involved and we have an alloy. For example, we could have iron and carbon, which is common steel. So carbon being a nonmetal, iron being a metal, does not have to be. So how do we go about creating an alloy? Because typically we're dealing with mixing a bunch of solids, then we have to melt those solids together and then cool it back down. And I give you a couple common examples of these. Something like brass, which is copper and zinc, or bronze, which is copper and tin, or sterling silver, which is silver and copper, and steel, which is iron, copper, and several other ingredients, depending upon the particular flavor of steel in question. So why do we use alloys? Why are they so important to us? And because we can produce properties that are often superior to the pure element that we began with. So while we may be able to predict the general properties of an alloy, alloys are created experimentally by experimenting with various percentages of ingredients and testing the resulting properties. So we'll alter the percentages, add a little bit more of one ingredient, add a little bit less of another ingredient, and we examine the properties that are formed. And we can often get properties that are much better than a pure element. Almost everything that we use in a metal form is some form of an alloy rather than a pure element. So there's two major classes of alloys. One would be a substitutional alloy, and the second would be an interstitial alloy. And then if we want to think about a third class, which is a blend of both of those previous two, it's substitutional and interstitial. So substitutional, just as the name implies, is we are substituting things. So we're substituting one atom for another. And here would be where my ingredients are about the same size. Here I could picture maybe if I had ping pong balls and golf balls, that they're pretty similar in size. And you could substitute a ping pong ball for a golf ball if you had them all laid out on the floor and not alter your crystalline structure very much. A good example of this would be something like brass and bronze. All right, an interstitial alloy is where we have significant different atomic sizes, and my smaller atoms are able to fit into the spaces between the larger atoms. An example of this would be steel. Carbon is significantly smaller than iron, and it would be able to fit into the places between those iron atoms. Here we're able to pack quite a few more atoms into one spot, and that can definitely impact my physical properties. And then the third type is that blending of both substitutional and interstitial. So we're substituting and putting other atoms in between the spaces as well. And stainless steel would be an example of this, where carbon atoms fit between the iron, and some iron is substituted with nickel and chromium. The image helps get a better example of that. Here is a pure metal, where it's all the same different element. Let's say this is iron as an example. This would be a substitutional alloy, where they're close enough in size that the different blue atoms here are substituted into the places of the original red atoms, and it still has that same crystalline structure. Here would be an interstitial alloy, where these smaller green atoms are able to fit in between the spaces of the original atom. So interstitial, it's fitting in the spaces. And then lastly, this is a combination of both substitutional and interstitial. Alright, so that ends the video on metallic bonds. The last video coming up will be on intermolecular forces of attraction.